I'm pleased to introduce our speaker today. Betsy Beise is a professor of physics and associate provost for academic planning at the University of Maryland, where her responsibilities include oversight and development of new academic programs and oversight of undergraduate and graduate curriculum. She came to the University of Maryland as an assistant professor after working as a research associate at the Kellogg Research Lab, Willie Fowler's lab at Caltech, and for that she won a number of awards. She received the Maria Gerpert Mayer Award from the APS for recognizing the outstanding achievement by a woman physicist in the early years of their career. She served a time as the program director for nuclear physics at the National Science Foundation, and has earned a number of awards. Let's do all.
Good. Thank you very much, Jack. You don't have to clap. Clap now, so you won't have to worry about it later. Yes, right. Yeah. It's a pleasure to be here. This is an honor to be in a room full of what I'm sure is a tremendous amount of wisdom. As Jack said, my name is Betsy Beise, and my day job now is in administration at the university, so I haven't had as much time as I would like to spend on physics research in the last 3 or 4 years or so, but I am also on the faculty in the physics department. And I was honored a year or so ago to be one of 5 faculty across campus who were given the award of a Distinguished Scholar Teacher, which was a great honor for me, especially because I hadn't been in the classroom for a couple of years. But as a result of that, I had to give a colloquium that was supposed to be broadly available to folks around campus. And we also had to have a little bit of a catchy title. So this is the best I could do, which was the matter of our matter, that is the matter that makes up us, and tales from nuclear science. And so what I decided to do for that talk was to kind of go broad but not very deep, and I'm going to do that today as well, and base my talk on, I also served on the most recent National Academy decadal study for nuclear science, and we just recently published the results of that. It's called NP 2010, even though this is 2013. We did start in 2010, so.
Time runs slower.
Yeah, that's right. But if you're interested, this is a very nice kind of forward-looking view of the breadth of the field of nuclear science at this point, and a particular attention this time was made to how the field of nuclear science serves society, given all of the things that are going on, with concerns about funding and so forth. So I will draw from this as we talk. And as I said, my talk will be fairly broad and not very deep, and there certainly will be places where I don't have a lot of expertise, and I'm guessing there are people in the room who might. So either feel free to correct me or speak up if I don't get something right, or elaborate if I haven't gone deep enough. Can I ask, is anybody in here from the field of nuclear science or nuclear physics? Nuclear science or physics or applied nuclear physics? Or, okay.
You're safe.
Yeah. Okay. So what I started and the first couple of slides of this talk will probably be a little bit too low, and then we'll move on from there. What I started already in a little bit dangerous waters for myself, since, as I mentioned in the talk that I had given, I have sometimes trouble finding the moon at night. But this is an example of a nebula, an exploding star. I think I did hear we have some astronomers or astrophysicists in the room. And the main point I wanted to make about this is the cloud of gas that emerges from this. I think we know there's a lot of excitement these days about how little of the matter of the universe is visible matter. And this is an example of some of that visible matter. And as probably most of you know, we believe now, or it is believed now, that a large fraction of the matter energy of the universe is dark energy, with another 25% or so coming from this dark matter, which is not visible. And then this tiny 4% is the visible matter. But in many ways, it's the most important matter of the universe, because it's what we're made of, and it's what drives the evolution of stars and planets and so forth. And so this was just an example to show the cloud of mostly hydrogen and helium, which make up almost all of the visible matter of the universe. And that's the piece of the universe that I would focus on today. So I think I already said I'm drawing largely for nuclear science on reports that have been written over the years about what are the major questions driving the field, and what are the best tools, how do we design the best tools to answer some of those questions. And that's kind of the theme of this talk. And I already mentioned this report. The nuclear science community actually has a pretty good reputation for being a grassroots organization that kind of works up from the bottom to decide collectively what are the best tools to drive the field forward. And the most recent of these is the 2007 long-range plan. We're probably going to go through another long-range planning exercise in another year or two. Some of the facilities that I'm talking about are the result of this planning process as we move forward. So again, this was meant to be a general talk. So this, what I tried to do when I was giving this talk at Maryland was just identify a little bit how we know about the nucleus of the atom. And the timing was pretty good because not too long ago was just 100 years since the discovery of the nucleus of the atom by Ernest Rutherford. I'm not very good at history, particularly history of science, and I was kind of didn't realize that Rutherford received the Nobel Prize in Chemistry well before this discovery. I didn't know that most of his efforts were about. So here's where I imagine there's more expertise in the room than I have, which is when I talk about some of these historical things, you may actually know more about some of these people in history than I do. I know when I quit my day job, one of the things I'd be interested in doing is learning more about, digging more deeply into some of this history. But anyway, so his Nobel Prize in Chemistry was for the investigations of radioactivity and disintegration and so forth. And Rutherford scattering is a theme that I'll come back to, but of course all of you know well probably that the key idea was by doing a scattering experiment, it was anticipated if the atom were just a uniform distribution of matter that scattering would be mostly in the forward direction, and by identifying these backward scattering pieces was a clear indication that there was some small massive something at the center of the atom, which eventually became known as the nucleus, with constituents which are neutrons and protons. And part of the very interesting story, of course, is that in the nucleus of an atom, there are particularly heavy nuclei, there are many more neutrons than protons because of Coulomb repulsion. And so you can get these distributions of these objects that are quite unusual. And I'll talk a little bit about that as we go. Another hat that I wear at the University of Maryland is I'm the co-PI of a grant called an advanced grant, which is designed to improve recruitment and retention of women scientists. And so one of the other themes that I picked up from my talk was to at least highlight a couple of women from nuclear science who are historically involved in nuclear science. And interestingly, one of them, does anybody know Harriet Brooks or know of her historically? She was Rutherford's first graduate student at McGill University. And Rutherford characterized her as essentially the next Marie Curie. She was apparently a brilliant student. She only completed her master's degree, and then she went off to teach, which was not uncommon for a woman scientist. And she actually had to quit her teaching job when she got married, because you were allowed to be married and have a professional position at the same time. So she left the field, but well before she left the field, she actually worked on the decay chains of uranium and thorium, and discovered radon. So she was one of the early pioneers of understanding radioactivity. And part of the reason I show this is just, again, that was about the time at which what we know are the kind of radioactive decay modes were classified in terms of either alpha decay, where two protons and 2 neutrons come out and lead to another a nucleus with 2 fewer protons and 2 fewer neutrons, or beta decay, which transitions 1 neutron into a proton with the release of a neutrino and energy. And the neutron decay is not really in here, but you can also go in that direction by emitting neutrons. So that language kind of appeared around that time. So the rest of the talk I've sort of organized around what I would call 3 tails, which are the tails of what I would call visible matter. And one of the very interesting features of nuclear science is that it spans pretty much the entire timescale of the universe. There are everywhere from the Big Bang and the early creation of strongly interacting matter in the first few, what is believed to be the first few microseconds of the universe, to the formation of heavy elements in stars, which was many, many billions of years later. And somewhere in the middle, we don't know exactly what that time scale is, but not long after this first few microseconds, as the universe cooled, the first neutrons and protons began to coalesce together, and light elements started to be formed. So I'll kind of focus on 3 regions, and again, very broad and not very deep, which are this very early region. Actually, I'll start at this end, which are what we might know about heavy elements and what we would like to know. Then I'll go back to the very beginning to talk a little bit about what we're trying to learn about the formation of matter in the earliest stages of the universe. And then I'll finish up in the area where I spent most of my career, which is this first few minutes and what we are trying to understand about the structure of protons and neutrons and light nuclei. So the first tail is, the question surrounding the first tail is how were elements such as gold, platinum, uranium, and anything really heavier than iron, the heaviest stable closed shell nucleus. And the other question surrounding that is, why is it that some elements are stable and others are not? So again, this is far too low for this audience, but the way I introduced this topic to the other audience was to remind people of what the periodic table looks like and how atoms are organized in terms of shell structures, and that drives a lot of chemistry. So all the single electron, 1 electron atoms are on this side, and all the noble gases are on that side. And the two atoms that are liquid at room temperature are highlighted in a different color, and they're characterized by a name and numbers of protons and total mass of the nucleus, of the atom, sorry. So it would be, and you probably all know well the story of trying to use this same scheme to characterize the structure of nuclei and the development of what appeared to be a shell model describing the energy levels of neutrons and protons that describe the masses and excited states of nuclei. And Maria Guppert-Meyer won the Nobel Prize in Physics in 1963 for that organization of nuclear structure. One kind of interesting fact about that is the so-called magic nuclei, which are closed shells where, for example, in oxygen, where the 8 protons are organized into a closed S and a closed P shell. These so-called magic nuclei don't really correspond to any organizational scheme on the periodic table so much. So that's kind of a puzzle, and that puzzle was eventually solved by understanding that a nucleus has a much larger spin-orbit contribution to its structure than, first of all, a much larger spin-orbit contribution which rearranges the energy levels, and also that neutrons play an important role, and filling up shells in neutrons play an important role in the stability of the nuclei. So for example, lead, while it has 82 protons, it has 126 neutrons. So it's a much different looking thing than an atom that has equal numbers of protons and electrons. One of the more, this periodic table keeps changing. So fairly recently, as late as I think it was 2011, this whole string of very heavy nuclei, way out in what's considered to be perhaps an island of stability in nuclei, have been discovered. Ones like flerovium, which is named after the Flerov Institute in Russia, and livermorium, named after the same group or collaborative group that discovered these other elements. So even today, the periodic table continues to change a little bit. And just by way of reference, here is uranium and thorium down in this actinide level. Few other, just one more highlight about some of the famous women in nuclear science in the early days. Many of you are familiar probably with Lisa Meitner, who actually discovered that element that's in between uranium and thorium in the early 1920s, and then is credited, although not with the Nobel Prize, credited with developing an explanation for nuclear fission and how elements transform from one to another, along with the experiments of Otto Hahn. So she did not win a Nobel Prize, but she did get an element named after her, which may actually be better. It's a little more probably memorable.
Otto Hahn got one too.
Yes, he did. Right. And then the other interesting element, is francium, which is that heaviest noble gas, and also shortest lived noble gas, discovered by Marguerite Perret. And I guess the story behind this was there was quite a lot of controversy because somebody else had thought they discovered it, and there was a lot of back and forth for a while. And finally, she was determined to be the correct and identified this. And then the question was what to name it. And apparently there had already, by then, germanium had already been discovered. And France wanted an element named after it, so it became francium. So, and francium is interesting. I don't know if you've had my colleague Luis Orozco come here or not from the University of Maryland, but he's a person who knows quite a lot about this particular element. It's interesting because there are quite a number of isotopes, and it's very neutron rich. And if you do atomic parity violation measurements on francium, there's quite a lot you can learn by looking at trapping these elements and then looking at how the transitions between atomic states vary as a function of how many neutrons are in that nucleus. So if you're looking for another speaker, he would be a great choice. Okay, so the periodic table of nuclei is arguably a lot more complicated than the periodic table of elements, the chemistry table. And this kind of characterizes it a little bit. The black squares here are the known stable elements, those ones that are in the periodic table of the chemistry periodic table. Elements that have, or nuclei that have actually been seen are kind of in this yellow band surrounding. And more protons goes this way, more neutrons go that way. And this characteristic feature of stability is that if you start down in these very light ones, this 2 plus 2 is helium, this is oxygen. By the time you get up to tin, I guess is here, nickel's in the middle of that, 28. The number of neutrons is much greater than the number of protons to make a stable nucleus, again, because of that Coulomb repulsion of the protons. But so this line doesn't go straight up in terms of even numbers of neutrons and protons. The big question is what happens, where is the limit of stability going out in this direction? It is generally thought that processes that happen out in this direction are the ones that create the stable elements that are found in, the heavy elements that are found in the universe. So a big push in the field these days is to try to learn more both about just the existence of elements out here, but also what their structure looks like, because the structure derives how quickly they decay and how they might drive processes that would create the abundances that we see here. So I'll say a little bit about more than that. And the other interesting feature, of course, is with neutrons, you can, because the strong force is strongly binding, it is possible to get pure neutron matter, and hypothetically, and so neutron stars are a possibility of existence. So just to kind of drive home the point of how you might make these black stable elements, I'm going to show you, this is a little simulation created by 3 colleagues, one an experimentalist, Hendrik Schatz at Michigan State University, Ani Abrahamian, who's at the University of Notre Dame, and Brad Meyer, who's a theorist at Clemson University. And what they tried to do was start with some simple assumptions and then use measured masses of the nuclei that are known and the known radioactive decay rates for some of those and predict what the path might be to create these black ones. So it's a little hard to see this down here, but we're at 1.7 seconds now. So this is from 0 to about 10 seconds, or 10 minutes, I think, beginning of the universe. And just from the information they know, this is how they might postulate how you get from just creating these through hot thermal processes and then bringing them back home. And one of the outcomes of this kind of analysis is that there are 2 very key nuclei, nickel and the isotopes of nickel here, and tin, and the isotopes of tin here that drive the way in which and the rate at which these processes get generated. So there's a lot of interest in identifying those, what's going on with those 2 nuclei in particular in the field. Ideally, in principle, you could make, because you can make stable nuclei with lots of neutrons, you can imagine just adding neutrons in and making whatever you want and then watching it decay and so forth. But of course, experimentally, that's very, very challenging to do. One of the premier places to do this work in the United States is at Michigan State at the National Superconducting Cyclotron Laboratory. It's right on the Michigan State campus if you haven't been there. And it's a pretty clever arrangement of 2 cyclotrons and then a so-called fragmentation facility where you start with some source, accelerate it, strip the electrons off, and then accelerate it some more, and then bombard another target that produces what you're interested in. And in this case, it was nickel-78. And then you have to very efficiently transport that nickel to place where you can actually analyze it or detect it in a detector system. And Michigan State has done an outstanding job of creating this kind of facility, and quite a lot of the work in this field is done at that location, also at Oak Ridge, at the and at Argonne National Laboratory. So one particular example is the study of the nickel isotopes, and with a good transmission, you can identify at the end of all of this just a very few of these nickel-78 isotopes and try to map out the abundance of these, and also, if you can collect enough of them, try to measure the lifetimes of these unstable, very unstable nuclei. The structure of these nuclei also has an impact on what we know about abundances, and here's a place where I'm treading on very thin ground myself because I don't know this field so well. But the basic concept is that, if you had sort of this basic atomic shell model like atoms are, it's not so hard to predict what the energy levels are for 1-electron atoms. Maybe for multi-electron atoms, it gets harder. For these closed shell nuclei that are stable, particularly the heavy ones, this is nickel and tin and lead, that's numbers of neutrons, these levels get all mixed up. And that actually drives understanding how those energy levels are organized, helps understand what the decays to other states are going to be. And that eventually would drive what the abundances of those elements would be in the universe. And it's now possible to compare these nuclear structure calculations, abundances from these nuclear structure calculations, to actual observational data. And one of the key features is the points here are observation. And if you don't have this pronounced shell structure, if all these levels are mixed up together, then the abundances are much higher in these particular cases, very closed shell nuclei cases. So we're starting to kind of understand those processes. The next generation of this field is to, recommended by the Nuclear Science Long Range Plan, is to build a facility here in the United States to create these rare isotope beams. So, and this would happen at the on the Michigan State campus again. And now, instead of the National Science Foundation funding it, the Department of Energy would be contracting this machine. I'm not going to say very much about it other than it's on the campus, and the idea, again, is to be able to produce these very neutron-rich, very short-lived isotopes to try to understand a little better what's going on in this side of this periodic table. And this graph down here just shows the dark blue are the isotopes that actually have been seen, and the blue here, the light blue, are the isotopes that are postulated to exist by theory, and the green is the part that this new facility would be able to fill in. So at the very light nuclei, a lot of work has been done, but it's this region out here that's very hard to see. And then there's always the question of whether there is this little island of stability well past lead, and that's where those very heavy elements are now identified.
About 120 or thereabouts.
Protons, yes, yes. Okay, so that's the first tail. Second tail is another area of focus in nuclear science, which has probably some of you may know a lot more about just because it's been a lot more in the news, is the efforts to try to understand what the properties of matter were before the creation of protons and neutrons, when the universe was hot enough that the substructure of neutrons and protons, the quarks and gluons that make up almost all of the mass of those neutrons and protons. At what point in time was the universe hot enough that those were free, and what was the state of that matter at the time that those were not interacting to each other? So when did the strong interaction become an important player in the understanding of matter in the universe? And this is generally thought to be somewhere in the first few microseconds. And this is the purview of the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, where beams of gold nuclei are collided, or other heavy elements are collided with each other to try to create enough temperature, enough a state of matter that could simulate what occurred in the earliest stages of the universe. So you need lots and lots of neutrons and protons, and you need them to be highly relativistic and very energetic. So this is kind of a picture of what that collision might look like. And of course, because these are relativistic, instead of being spherical, they're length contracted and smashing into each other. And then the hope is that what you're seeing is there's so much energy in that collision that the quarks and gluons start coming, the neutrons and protons start dissolving, and you end up with a soup of quarks and gluons. And then as they go out, you try to look in a detector system to look at the remnants of that process. This is very, the other APS headquarters is right next door. I'm sure some of you have been there, and you can actually see the heavy, RIC from space. It's big enough. This is just one more slide of the same kind of thing, and this was one of the first events that was published. It was back in the late 90s, I think, of an event seen in this detector system. So when after that collision took place, thousands of particles would come out into this detector system, and the real challenge there is to try to identify them, to actually recreate the tracks from all of those events and try to see if that helps you understand what happened in the center here. So there's been an enormous amount of data from the RIC experiments, and very exciting results, and lots of controversy about what they actually mean. Generally speaking, the general conclusion seems to be that there is some kind of a quark-gluon phase, plasma phase, but maybe it's more like a liquid than a plasma. It seems to behave like an almost perfect liquid with almost no viscosity. And understanding why that's the case has been one of the major challenges of the field in the last five or 8 years or so. And this is just a little graphic to kind of show what you see in the detector as you go back in time, how you might be able to simulate what the early stages, if you can reconstruct what that state of matter was right at the collision, what you're trying to do is reconstruct kind of a little, an image of what the universe might have been like in its own early stages. So again, I'm starting to speak way outside of my expertise, so I can't speak very deeply about this. But one of the real advantages of a facility like RIC is the ability to not only accelerate gold, but I think they've also done calcium, but you can also accelerate very light nuclei like individual protons or deuterium and compare the results from, say, a gold-gold collision versus a deuterium-gold collision. Deuterium, 1 neutron, 1 proton, very light, small nucleus. And this was, again, one of the early results that showed in the black here are the what you would see in two back-to-back jets of particles coming out of the detector from a proton-proton collision. So that they collide and then things come back out again. Versus deuterium gold, where there's one light and one heavy thing, they collide and stuff comes back out again. Versus two very, very heavy things where the collision takes place and one jet gets out but the other does not. So the idea there is that, so that's the blue stars here. So the idea here is that one side of the stuff coming out has had to interact with so much matter that it's basically been attenuated. It's been stuck getting out of that very strongly interacting quark-gluon soup. And that was one of the early indicators that there's very definitively something unusual happening in this matter. So RIC and also new experiments at the Large Hadron Collider are now working hard to try to really understand this in a more quantitative way through collisions at higher energies at the Large Hadron Collider and through continued experiments at RIC. The other advantage, a very nice feature of RIC are these proton-proton collisions, is that you can polarize the protons and you can align their spins and you can do all kinds of other suite of experiments to try to understand, using that information, what's going on in the interior of the proton, of a cold proton. And I'll talk a little bit more about that because that leads to the next tale. Am I talking too fast, too loud, too quiet? Questions?
Yeah.
Discussion?
Very
okay,
good.
Thank you.
Please
I don't want to talk, just be a talking head. Okay. Okay, so the last of the three tales is what I call the tale of formation, which is how do we know, what do we know about going from this state of quarks and gluons to neutrons and protons, and then ultimately to light nuclei and the formation of stars and through the creation of carbon and nitrogen and oxygen and then to heavy elements. So what do we know about this little phase right in here? And how can we develop a real quantitative description of how we go from free quarks and gluons to confined quarks and gluons in a nucleon? So I'm going to talk a little bit more about that step. And when I'm talking to students about this, one of the things that I try to highlight is how unusual the strong force is. You know, if you think of an atom and you try to put together, say, the hydrogen atom, you have this proton and you have this electron and you have a little bit of binding energy, and you can pretty much describe the mass of the hydrogen atom just from those two masses plus this little tiny bit extra, 13.6 electron volts, compared with the GeV mass of hydrogen. And you have a description, and then you can use kind of successive approximations or perturbation theory to refine that to very high precision. If you try to do that with say a proton, and you start with its fundamental constituents, which are up and down quarks, and you can take the charge, you can, the idea that quarks had fractional charge came out of the fact that the charges had to add up to the charge of a proton or the charge of a neutron. So if you take two up quarks that have charges of plus 2/3 and a down quark of charge minus 1/3, you add them up, you get 1, and you do the same thing for the neutron, and you'll get 0. But if you try to take their masses and do that same thing, you only get maybe less than 1% of the mass of the proton. So all of the mass of the proton comes from the binding energy, effectively, comes from this field soup of gluons, as they're called, which is basically the mediator of the strong interaction that holds the proton together. So that's a very, very characteristically different beast than an atom. And that makes it very challenging to try to understand what's going on inside, but also very interesting to try to understand what's going on inside. So, so one picture, the very simple quark model picture of a proton would be just these three things that have that are bound together by a force, these three quarks that are bound together by a force. If you try to look a little bit more deeply, you'll see that these things themselves are really not the fundamental constituents, but they're made up of many, many, many quarks and gluons, and they kind of maybe organize themselves into these so-called valence quarks. But there's lots and lots of energy and quark-antiquark pairs being produced in order to, through production and annihilation, just that energy bubbling around and so forth. And so then the deeper you go, the more you kind of see that there's just a very dynamic process going on inside of the proton, and trying to understand that is a challenge, is a very big computational challenge, for one thing. Yes?
So this is something I've been thinking about since I was 2. So what is your idea of mass? What is mass?
Well, that's beyond my pay grade to answer. But in this case, I think of it as E equals mc squared, rest mass. So, so the mass of the proton is made of the matter mass of the constituents plus the binding energy that holds it together, just like if you were to the mass of a hydrogen atom. So this is actually, this little cartoon down here is actually a simulation done with what's called Lattice Qcd. So it's a computational simulation of what might be happening inside a proton. And these are fields of gluons that are being created and then annihilated again. So much of the theoretical advance in this field is driven by our now ability to do very, very sophisticated computation because of how the computing industry has expanded so much over the years.
Well, one usually thinks that binding energy is negative, but in this case it must be positive.
You do have to sort of think of it that way, yes. It's a much greater contribution. Well, it's a little hard to think about that way because you think of it as negative because the Coulomb force is attractive, right, between a positive and a negative charge. That's what or in the gravitational case, the gravitational force is attractive. Yeah. So the strong force is a little bit more complicated. It's attractive in some regions and repulsive in others. So if you bring two quarks together too closely, there'll be so much energy there that they will create new. So the gluons then have to have some kind of a mass field associated with them, yeah, or an energy associated with them that.
They're very heavy then, compared to.
I mean, they are. That's the other very unique characteristic is these gluons. If you think of a photon, say an atom being held together through the exchange of a photon, that photon is massless, and it also has no charge. So it doesn't interact. It only mediates the interaction. It doesn't actually feel its own interaction. Gluon has the property of color that is the property that of the interaction itself. So you could imagine, for example, making a bound state of only gluons, a strong interaction bound state that's only these gluons. So I don't think of it as the rest mass of the gluon, it's the energy associated with, the binding energy associated with.
No such thing as a free gluon.
So far, hasn't been discovered, right? And, but people are looking for these so-called glue ball states. So far not discovered, but it's hypothetically could exist. There's nothing that would keep that from existing.
What are the masses of the free quarks?
So again, that's in the standard model. So they haven't been measured, so I'm trying to be careful. I'm an experimentalist. But typically in the standard model, they're thought to be a few MeV, few mega electron volts. So a few times the mass of an electron. So if you just take those three things, you would just get, something that's only a 10 MeV or something like that, compared with 1,000 times heavier proton.
1.3 and 1.8, something like that.
Of 1.3.
I mean, the mass
of the quarks.
Part.
Yeah, okay, so you may have a better sense than yeah, right. So it's a theoretical number at this point. It's not a measured number. Yeah. Okay. So a lot of the field of this area is really trying to quantify with high precision what the properties of neutrons and protons are in these light nuclei at a wide range of distance scales to try to understand how to get from here to there. And so one example of that is trying to understand the proton's magnetic moment. So again, when I'm talking to students, I try to remind them that we know proton magnetic moment is something that anybody who's had an MRI has some experience with, because the water in your body is the magnetic. When you put your body in a magnetic field, the magnetic moment of the protons in the water is what responds to that magnetic field. And so the fact that the proton has an extraordinarily large magnetic moment than what you would expect for a point particle is what allows this to happen. Very interesting. And that's been known for a long time, of course. And we know with very incredible experimental precision what these magnetic moments of neutrons and protons are. But theoretically, it's extremely challenging to calculate what they are. And the state of the art is really maybe one, possibly two significant digits, but really one. And that's using fairly complex computational techniques to try to get there. So the experimentalists are kind of ahead of the game in this because it's possible to do these very precise measurements. And doing them, trying to understand the magnetization distribution inside a nucleon or the charge distribution inside a nucleon will help try to answer this question of how do these constituents add up to create that situation. And of course, this is again a field that's been active for a long time, since the 1950s when early experiments were done at Stanford, and then there was a suite of experiments at SLAC to try to make these measurements. And they're typically done with an electron beam, a nice point-like, not strongly interacting particle that doesn't cause, that allows you to measure things about the strong interaction without the probe being involved in the interaction except through its charge. And then if you can vary the energy of the electron beam, you essentially vary the wavelength of wavelength of that electron, which allows you to probe different spatial distances. And it turns out a good range to study kind of the size of a neutron or proton is a beam of somewhere between 1 giga-electron volts and 10 giga-electron volts. If you get much higher than that, then you don't get much interaction, and other things, you start to worry about other things. But if you get right in that region, you can map out fairly carefully the distributions of the charge and the magnetism inside these particles. So standard experiment is to take a beam, hit a target, and then look at the again, this is just Rutherford scattering all over again. You just look at the distribution and energy and angle of the scattered particles to reconstruct what was going on in here. And the premier place in the world to do these experiments, I think you've had a tour. Anybody gone? Some folks have taken a tour down there. Is Jefferson Lab, which is in Newport News, Virginia. It was completed in about 1995. First experiments started in about 1995, and it's been active now, very productive over the last 20 years. The beam, electron beam, gets generated, in a while since I looked at this, so yeah, I would say here. And there's kind of a racetrack to it. So there are 2 linear accelerators connected by arcs, and you can go around up to 5 times in order to, and then dump into 3 experimental areas and get a beam up to about 6 GeV. And this is just an example of how the beams are actually stacked on top of each other in these arcs. Jefferson Lab is right, in fact, in the middle of a major upgrade to double its energy from 6 GeV to 12 GeV by adding some additional accelerating cavities along the sides here. These are all superconducting, so the energy power dissipation is pretty low. It's a pretty efficient facility, with the exception of having to create all of this liquid helium to keep the accelerator cavities. So their plan is to add these new cryomodules here, and they've made huge improvements in the accelerating capability of the ones that are in there, which has already raised the energy of the beam. And then there's there's a 4th hall being added to do a new suite of experiments off to the side here. So I won't say very much about this program. I have 1 slide, I think, to talk about this program. I'll mostly talk a little bit, just 1 or 2 slides on some key results that have come from the existing facility. And this is just an example of one of the detector systems in one of the 3 experimental halls. So I took that same picture and turned it around. I couldn't turn the words around, but turned it around. So here's the beam coming in. Here's a target area. And then this is a large magnetic spectrometer, and the detectors sit way up at the top here. So the scattered particles get bent, and then you can move, you can swing this detector around very easily. And there are actually 2 of them, so you can look at 2 things coming out at the same time. Very, very precise detector package there, very high resolution. And so here's just one snapshot example of the kind of thing that has been learned since Jefferson Lab. And that is about the charge and magnetism distributions in the proton and the neutron. So this graph is hard to see. The horizontal axis is basically smaller distances go in this direction. So the higher energy you have, or the more momentum you can transfer in the interaction, the shorter distances you can see. And before Jefferson Lab was built, these open red circles up here is kind of what the state of the art was. And what we're looking at is the ratio of the charge distribution in a proton to its magnetization. So you might think that would just be the same. And for many decades, if you looked in textbooks, you would see, for 2-3 decades, you would see probably the assumption that those were actually the same based on these data that mostly came from SLAC, from Stanford Linear Accelerator back in the 1970s through the 80s. Jefferson Lab had the ability to, first of all, do polarized targets and polarize the electron beam, so you can line their spins up and do some interference type experiments, and also do this with very high precision. And this was the result. And so for a long time, when this first data came out, there was a lot of discussion about why these 2 results were different from each other, and were these wrong? This was a new technique. And I think now it's generally believed that these are correct, and there are some effects, interference effects that are clouding these open circle data. And this leads to a very precise understanding of what these distributions are like. And the interesting thing is that the magnetization seems to be very different than the distribution of magnetization seems to be very different. And that may be because there's some orbital angular momentum of these quarks that are causing some extra magnetism or less magnetism or different distribution. So it's a new result. So this is actually a calculation of what that distribution would look like if you were the beam and you were looking straight at the target. So it's a transverse distribution. So you can kind of see the proton is all the charge is in the middle and is a drop off on the sides, kind of like you would expect. In the case of a neutron, this is actually a neutron that's oriented in some direction. So what you're seeing are the currents, the orbital motion of the interior constituents causing some change in the distribution of the charge. And then what this is now the state of the art for what we know about the distribution of charge and magnetism in the proton. So these bands are actually the uncertainties. So we know this extremely well for both the charge and the magnetism. And similar information, in fact, is now available for the neutron. So we actually know the neutron's charge distribution very well and its magnetization very well. Maybe I'll skip. It's getting late, so I'm going to skip a topic.
Go ahead.
No? Should I not skip? You're not bored yet?
Yeah, we want to hear.
Okay. All right, if you're not bored yet. Another feature of having this really exquisite electron beam that one can line up, polarize either clockwise or anti-clockwise, is to do parity non-conservation experiments. So when you can make a lot of polarized electrons and when you know their properties extremely well, you can actually use the beam scattering from an unpolarized target. You would get a difference in count rate if there were a handedness to the interaction. And most of you probably know that's a signature. That parity non-conservation is a signature of the weak interaction, a different force. But it's a force that the electron feels, and therefore the electron can interact with the target that way. And it turns out you learn yet different information about the internal structure of the neutrons and protons from that. So there's been a whole series. This, again, was a pioneering experiment at SLAC, of course, in the early 1970s. But some kind of figure of merit of what you can do now compared with what you can do then is many, many orders of magnitude different. It's very qualitatively different. And there's been a large program of experiments at Jefferson Lab to use this to try to understand other characteristics about the internal structure of neutrons and protons, but also to do precision measurements of the standard model for electroweak interactions. And one of the features of this beam is that you can determine whether, for example, the position of the beam on target differs in one-handedness versus the other-handedness to nanometers. So it's incredible precision that you can get from this very high-quality beam. So the science goals for using the weak interaction are first to look at the internal structure of the proton in a different way than just straight scattering, do these precision standard model tests, and turns out also because the weak interaction actually prefers neutrons over protons. So you can learn a lot about distributions of neutrons from using the weak interaction. And all three of those types of experiments have now been done at Jefferson Lab. This is just one example of an experiment that completed back in 2009 that I was involved in. It's called the G0 experiment. And here the beam would be coming in from this side. There's a large toroidal magnet, superconducting magnet back here, and there's a liquid hydrogen target sitting in the middle there, and then we looked at particles that were moving in the backward direction in this detector stack of about 500 detector modules, two layers, 500 in this layer and some much smaller number in that layer. This is my colleague, Doug Beck at the University of Illinois. He actually just won a prize from the Southeastern University Research Association as their distinguished nuclear physicist. He shared with another scientist, Paul Sauter from Syracuse University, for their work on parity violation experiments. So we're very proud of him for that. what this kind of work, an example of one of the things that comes out of this kind of work is to pick apart the contributions of up and down quarks, but also strange quarks in determining the interior structure of the neutron and proton. And a whole suite of measurements finally concluded that with very high precision we can say now that a very, very small part of the proton's magnetism might come from strange quarks, and essentially none of its charge would come. So anytime there's a strange quark in the proton, there's got to be an anti-strange that cancels out any contribution it might make to its charge. So just to kind of finish up and move forward, Jefferson Lab is undergoing an upgrade. This was the picture I showed you before, and now since then there's a whole new suite of technical facilities, and there's this new experimental hall is under construction here. This slide is from the director of the lab as of a couple months ago, so things are well. This is pretty recent. I'm not going to talk at all about the physics goals, but there's a white paper on the archive that describes the physics goals of what the upgrade will bring. It's more of the same at some level, but also some qualitatively new things, like looking for these very exotic bound states of quarks and glue, particularly two quarks and glue, so meson spectroscopy and these other things. And their hope is to actually turn the accelerator on relatively soon. They're being a little bit held back by the budget situation, both sequestration and the current budget situation. They've had to baseline the project a bit, but the hope is that they're on a good track and should be turning on fairly soon. So that might be another opportunity to go visit. Beyond 12 GeV, both Jefferson Lab and Rick are looking for what might be the next generation of studying QCD, the quantum chromodynamics, or the interaction between quarks and gluons. And so there's also a white paper about called the next Qcd Frontier, which would be to design colliding beams of electrons and light or heavy nuclei to continue to unravel the role of, most importantly, the role of gluons in this structure of creating the charge and magnetism, but also the spin of the proton. So I won't say much about that again. There are two, at present, there's kind of a concept paper for what this machine might look like, and both Jefferson Lab and Rick have developed designs for a first phase of that, and it is thought, it was an idea 5 years ago as what would be the future 15 years out, and we're getting a little bit closer to that. So I think it will probably emerge as a high priority of the field the next time we do a long-range planning process. I'll just mention, I took these slides from a former graduate student of mine, Tanya Horn, who's an assistant professor at Catholic University. So if you ever want to talk on this topic, she's not very far away and probably would be happy to give one to you, speak to you. So JLab, as I mentioned, Jefferson Lab has has a concept, as does Brookhaven, for how you might move forward. So this again is the satellite view that I had shown you with the new 12 GeV capabilities. And what they would have to do is build this very interesting complex suite of racetrack kind of ideas to create interaction points between the electron and the light ion. And they don't quite own all of this property, but they're working on it. So, yeah. I don't know if have any of you been in the Newport News area or lived there a long time ago or anything? So, it's absolutely astonishing how much it has changed in 20 years because of the existence of this facility. The growth in that area is just huge, and for better or worse, but it's really amazing. Okay, I was just going to finish up with, again, one of the things we tried to do in this report is give a little bit more focus on some of the societal applications to remind Congress that nuclear science is still relevant to the nation, and There are some obvious applications everybody knows about. Nuclear energy is one of them for sure. Border protection is another one, or homeland security. Being able to detect radiological material is obviously very important. But then the other spin-offs that people are a little bit less familiar, I'll just give one or two examples of. And one of them is medical imaging, that maybe people are pretty familiar with that, but the general public may be a little bit less familiar of the important advances that have taken place there. And high-performance computing is really driving what we are able to learn at this point in this field. And so the nuclear science community has been very much at the forefront of driving some of these techniques, both machines and computational techniques, to learn more about the strong interaction. So one example is a very well-known one, which is positron emission tomography, using particle detectors to image and the ability to make short-lived isotopes that can be traceable in your body and make them locally has become an important feature of this type of imaging. So nuclear science has contributed a lot to that by being able to make smaller and smaller machines that can create these isotopes. And fluorine is a particular example. I guess it gets taken up well in the brain, and so can be attached to glucose. So being able to make fluorine-18, it's short-lived, so being able to make it locally as opposed to making it somewhere and having to transport it is a tremendous value. Another example that is a little bit less well-known is in the field of electron scattering. To learn about the neutron, one of the techniques we use is to use polarized targets, where you can get rid of the charge effects and focus on the magnetic effects. And polarized helium-3 is 2 protons and a neutron, is a particularly nice example because the two protons tend to pair off. So a polarized helium-3 nucleus tends to look like a polarized neutron. And this is a lot of work, a lot of what we know about neutrons has come from using this as a target. And this is an example of what the target looks like at Jefferson Lab. It's a glass cell right in the middle here. You can also use polarized helium-3 for neutron scattering and imaging of magnetic materials, and that actually is done at NIST and also at Oak Ridge National Laboratory at the Spallation neutron source. And there's some nice work there. And if you're interested in a talk there, I can recommend a speaker. My husband works on this, so he's at NIST, so it's not very far away. And a third application is actually you can ingest this helium, and because it's a gas and it's got a large magnetic moment compared with, for example, water, it produces an MRI signal that's very large, so you can do low field magnetic imaging. And this is an example of R&D being done like that. It's particularly good for lung imaging. And so this is a patient who has ingested polarized helium-3, and you can see features of the lung that are very difficult to see in other ways. Brain imaging is another people use xenon to do brain imaging, but that one, it's a little harder to do lungs that way. So in fact, I think there in this book, there's an image of lung from a first responder from the September 11 attacks on New York, and you can see some of the damage from breathing in the material after the attack. So last example, and then I'll quit, is one of the things that's, this circles back to the very first slide about dark matter and trying to detect, either look at very, very rare decay processes or look for very rare things like dark matter. The segment of the field is moving underground to try to work in areas that are extremely low in radioactivity, where they're less, where they only have to worry about those uranium and thorium chains and nothing else. And so there's a lot of R&D going on to try to produce highly sensitive detectors. One collaboration is at the University of Washington, the Majorana collaboration. And this example comes from some work that they published after the earthquake at Fukushima. You know, that horrible incident where there was a huge flood, but there was also concern about what happened with the reactors. And all over the country, all over the world, I think people started turning on detectors to see what they could see. And this was one of a very sensitive example of what could be seen just about a week after the incident in Seattle. They turned the detector on. And the key feature here is the relative abundances of the isotopes that they were able to see at very, very low levels. So this is many thousand times lower than background radiation. The ratio of these indicated to them that the radioactivity was coming from the reactor and not from the spent fuel. So that was one thing that they could say right away out of these data. And then the second thing they could say, see if I get this right, and I put a note in here because I always have to read this one. The second thing was that they could see this iodine 131, but they did not see the iodine 133, which told them that the reactor had actually shut down safely. Now, I don't know exactly why that's the case. There may be somebody in the room who would understand that, but the features, the radiation features are pretty characteristic of whether a reactor is operating or not and what type of reactor and what fuel's in there. And so by looking at these elements, they could say quite a bit about what the state of the situation was when it was impossible to go inside and actually figure that out. And they could also see that this distribution was very, very different than what had been seen in Chernobyl. So they knew that this wasn't a reactor explosion. It was radioactivity coming from steam boiling off and not from the reactor itself exploding. So that's very valuable to be able to do that. And of course, the reason they're doing this is for totally different. It's to try to learn how to do experiments to detect very rare processes like neutrinoless double beta decay or look for dark matter. So that's kind of interesting. So I think that's as far as I was going to go. I just point out one of the reasons I do this is because it's fun to work with students, and these are some of the various collaborations and students that I've worked with over the years. So thank you very much for your attention. I'm sorry I went over a little bit.
Questions?
Yeah, I have a question about the rest mass of the neutrino.
Oh dear, okay.
And I wonder if there has been any direct, experimental observation to justify that, or whether it's a deduction from the fact that the neutrino has this internal oscillation.
I think we're still at, I'm not an expert, and I haven't been following the literature absolutely most recently, but I think we're still at the stage where we have an upper limit. And we know that there has to be mass from the oscillations, but so there is an experiment called Qcd, which is a tritium decay experiment that's operating.
One could say that because of the oscillation, there has to be some sort of internal
mixing
or proper time, but that's a deduction. That it's not a direct experimental verification in any way of a finite rest mass.
Right. So the direct detection experiment that I'm aware of is Qcd, which is a tritium decay experiment, and they are close to collecting data, but I don't. Yeah, I'm not sure. Okay. I don't know. I'm not fully versed in all of the efforts there.
Actually, I think
yeah.
we measure these differences in the squares of the masses. You
in the oscillation experiments, yeah, that's right.
Right, you don't.
Right, and so you don't know.
You get a mass difference.
That's right, squared.
Yeah.
So you don't even know which one's heavier, which one's lighter. That's right. And so the neutrinoless double beta decay is one possibility to help figure out the hierarchy of those. Yeah.
Most nuclear particles get their mass from interactions with the Higgs field. How about the neutrino?
Okay, now see, I'm a nuclear person. I'm not a particle person. So I think I'm not going to answer that because I'm not going to give you a cogent answer.
Is there
You need to, I mean the equivalent of a Higgs field?
Is there any answer these days?
I don't know that there's a a clear answer to that question yet. Yeah. There's a seesaw mechanism, which you can bring Robbie Mohapatra here and ask.
You
Yeah.
talked to the differences of the masses and
The oscillation rate depends
the
on,
oscillation rate, so then it's again a frequency they're measuring.
well,
And,
you know, for example, you
yeah,
know
yeah,
that,
well,
you know that all of the neutrinos that left the sun were electron neutrinos. And when you get to the Earth, only about a third of them are. So
it's,
you know the distance.
okay, so it's a frequency that's being directly measured or
Right.
to do.
Yeah.
There have been articles about that in Physics Today.
Yeah.
Um,
I can recommend a speaker.
Actually, the machine itself at Jefferson Lab, as I recall, we had a visit there sometime.
Yeah.
One reason, at least, that the beam quality can be so high is that it's continuous beam. Whereas,
Yeah.
the West Coast machine was
Pulsed.
not,
Yeah.
and that allows a very fine focus. And that in turn hinged, I think, upon the use of niobium superconducting chambers for the accelerator.
I think that's right. Yeah, I'm not an expert on the accelerator science, but yeah, I think that's right. And also, the other advance was the change from the technique for generating the electrons at the source.
Well, I didn't know that.
Years ago,
How does that
the
change?
typical thing to do would be to just use a thermionic emission kind of situation where you just boil them off and then collect them and move them. And these days, because of the desire for these polarized beams, people use a solid state technique where you shine a laser on a gallium arsenide crystal and you pull the electrons out, and they tend to make the emission coming out tends to be better characterized for accelerating and focusing. And then there have been a lot of advances in the types of materials in the material science to create high polarization and good emission for those. So JLab uses it even for the unpolarized beams, and there's a free electron laser there, and they use it for the emission for the source there too.
Getting a talk on the free electron lake. It's curious to me that I was entirely unaware of Jefferson Lab until we visited there about 2
Yeah.
years ago.
That's right.
And it doesn't seem to have been publicized nearly so much as
It's
previous accelerator laboratories have been. Were
Yeah.
you afraid that Congress would kill it?
No, I think it was just it was new, and yeah, I agree with you. I think the science community nuclear science committee could have done a better job at that.
more publicity of
Yeah.
results would be better.
Yeah. Yeah.
The success.
Yes, it's extraordinary how the quality of the beam is just incredible.
Perhaps you can rely on the community colleges to get the message out.
Yes.
Yeah.
Okay.
Because there's several of us here from a community
Good,
college.
good,
And
yeah.
we now have the majority of the undergraduates, at least for the first 2 years. But we want to pass them on to you.
Yes, I
because
know.
We want them to be successful.
Yes.
And I've got a woman in my class right now, she's brilliant.
Good. All right. Send her to me.
Which is in Germantown.
Yeah. Okay. Good.
You talked about Maria May and the shell model. Interesting anecdote. She was my first academic advisor. I took the nuclear structure parts from her.
From Maria Gopper-Meyer?
Yeah.
Oh, yeah.
And-
I heard
and-
that, since I'm on camera, I probably shouldn't repeat this, but what I heard from other people who had, is that she was a chain smoker, and she would hold a chalk in one hand and cigarette in the other, and sometimes would write on the board with the cigarette and smoke the chalk. I don't know if that's true, but,
I didn't see her do that.
I see. Okay.
Anyway, she said, well, during World War II, don't mind doing any research, we got to look at the data. And she started looking at the nuclei and all this.
yeah, it's a pretty interesting
She
story.
was a Fermi. Anyway, she showed it to Enrico Fermi, and he looked at it and said, is there any evidence of spin orbit coupling?
Yeah, there we go.
Now, because she was a smoker, Fermi wouldn't let her in his office, but he came to her office.
I see.
He got a phone call and went away. He came back, and she had done an estimate of the spin orbit coupling and said, yeah,
That's it.
that's what gives you the
Yeah.
magic numbers.
Yeah, I've heard that story before too.
Yeah,
That's
well,
pretty amazing. Yeah.
I heard it directly from
Yeah.
Maria.
Yeah. Wow.
Eugene Wigner once remarked that all her male colleagues were in love with her.
Well,
Yeah.
oh,
Wow.
she was really fast. But one of the other things she told us is,
Joe Meyer got her.
well, I knew. one of the other things she said she did is, she instead of memorizing the constants, she memorized the logarithms of them.
Oh, yeah.
She could do calculations like that.
That's a good idea.
Yeah.
Yeah, right.
Beta.
Yeah.
Where was this, at Chicago?
Yeah.
This was the University of California, San Diego.
Oh, I see.
Any other questions? One thing I wanted to note is that the reference that this is using, the National Academy's report, Exploring the Heart
This
of
report.
Matter.
Yes,
If you do a search on it, you can actually find it online.
yes.
And you can either purchase a paper copy of it, or you can download a PDF of it.
And there are also 2 little videos, and I think you're probably videos online as well.
Everything comes with this video.
Yeah,
The thing about a PDF, you put it on your computer, and you can always find it. You take a book and you put it on your shelf, you don't always find it. Pieces of paper, never.
Never. Books like.
yeah.
Okay.
Your shelf doesn't go down, and then the hard drive dies.
Well, what you do is you use a thumb drive.
Put on the cloud.
To make several backup copies. I do that like every few months.
We're on the cloud now.
Yeah,
On the
Right.
cloud.
Background, so
I
never
like to
lose
be
it.
on the ground.
In that case, they're gonna say something to look at.
Yeah, but who cares, we're not doing anything interested in.
Okay, well, thank you very much again.
Thank you for inviting me.
Thank you for a great
Thank you.
talk.